This is SciFi Talks. In our today's episode, we have a very special guest, Dr. Rajendra Pangeni. Dr. Pangeni is the Assistant Professor of Genomics at Nova Southeastern University. Dr. Pangeni is working on identifying genes that could be used as potential biomarkers and therapeutic targets in Gulf War illness. Dr. Pangeni is also a co-founder of NIVI, a non-profit organization based in Nepal.
So, Dr. Pangeni, how was your journey from Nepal to the university you are working in?
Thank you, Sudarshan. Thanks for the opportunity to talk with you. It's a great program. I have been able to go through your last episodes, and thank you so much. So, talking about my journey, I divide those in two parts. First, after my high school, that's basically 10th grade in Nepal, I moved to Mumbai for my higher secondary, that's 11th and 12th grade, and I did my undergraduate from Mumbai. Now, that was the first journey away from home for me for my higher studies. Then I returned to Nepal, and I worked in Nepal for a couple of years as a teacher in different schools and colleges. And then I moved to the UK for my second master's and PhD. So it's been a little tough in a way that my first kind of part of away from home was a lot of struggle during my undergrad and my senior high school, being away from home at such a young age. But my second part, moving to the UK for my master's, and I got into PhD to the US, has been pretty a little tough, of course, but it's been very enriching and rewarding.
How did you figure out the science you are working now? Did it happen in a flow, or how did you figure out or discover that this is your interest in the science you want to do, or you want to make an impact, or you want to invest your whole life or career in? So how did you figure out?
Thank you for the question. This is such an important question to me, to be very honest. Thank you so much. What happened was that during my school life, we were 7 siblings, and my dad used to bring medicines, because always one of other used to feel sick, fever. We used to have fever or flu, and then I used to read those labels, the medicine labels, and I somehow felt that when you talk about human life, the treatment, then curing the diseases, or something that has a direct impact in our lives, is the science. Of course, all of other fields have the direct impact, but so we had so many diseases those days. We used to have those vitamin that B day, polio drops, and other vaccinations and all these, and that all came from science and discoveries. So that somehow had a very deep impact on my thought process. That I think it's a science that I want to go further. Especially, I wanted to go to the medicine, and then after that, when I decided that I wanted to go to medicine, I didn't get into the medical school. We have a lot of background behind that, but then I chose to do a bachelor's in microbiology in Mumbai. So during my bachelor's, and then I realized something there is so much to be done if you say that. I think it's a cancer, being it's one of the very complex disease. So during my bachelor's, we didn't have a lot of courses, or we didn't have to do a lot on cancer, but we had to study a lot of diseases. And cancer was something that really fascinated me, and I wanted to go to cancer research. But looking at the epigenetics that I'm working now, maybe you'll come back to that later. Yeah. It's a kind of flow as well. When I was looking for my master's research project in the university, then that time, among the available projects that I was very interested, then I happened to do my master's research project with Dr. Mark Morris, who was the renowned kidney cancer epigeneticist. He worked on epigenetics of renal cell carcinoma, the kidney cancer, and that actually inspired me to move further in this field as a cancer epigenetics.
So let's talk about cancer a bit. So how do you define cancer in a very easy language? Because we always say that cancer is very complex, and you can't define cancer in one language. So there are different languages of defining cancer. But as a scientist, how do you define cancer for a layman person who wants to understand about it?
Cancer is basically, in one word or one sentence, let's say, it's a abnormal growth of cells, or it's an uncontrolled growth of cells. To talk a little more in detail, our body is made up of cells. Let's say we have skin cells. In our hair, we have hair cells. We have blood cells, and even blood cells. There's different types of blood cells. We talk about red blood cells, white blood cells. We have other kind of in the brain. We have neurons, or the brain cells, the neuronal cells. So our body is made up of different types of cells. We have trillions of cells in the body, and those cells produce the daughter cells. They divide, they grow, and they divide. But there is a limit of growth, so they cannot grow as big as a cricket ball. Let's say they grow in a certain. They are of course invisible by naked eye. You need to look them through the microscope, very powerful microscope. They're very small in size. So when they grow to a certain size, then they have to divide again. There's a limit of the size, and then there is a limitations of how fast they can divide. Now, when there is something wrong in the body, and then when they start dividing in an uncontrolled fashion or abnormally, and they can keep growing, and then without any control, then that leads to cancer. Therefore, when the cancer, a single cell becomes the cancer cell first the single cell has to gain that, a capacity to divide in an uncontrolled manner, abnormally, and all the cells that burn from cancer cells are the cancer cells, and they form a small lump or the masses, especially in solid tumors, that we call the cancer tumor or the cancer.
Oh, let's relate a little bit of epigenetics to the cancer. You said that you met a mentor who was related to the epigenetics, so you got interested in the epigenetics. But there are different approaches of working with the cancer, treating the cancer or curing the cancer. There are different approaches. But why are you satisfied by working with the epigenetic approach to solve the problems of the cancer, to solve the complexity of the cancer? Or do you think epigenetic is not enough? Or do you sometimes feel like, no, I should try to solve it with a different approach, or the genomic approach rather than the epigenetic approach? Do you feel like that, or are you very satisfied with this approach?
Thank you, Sudarshan. These amazing questions again. Something that somehow connected to my heart. Yes, that's a very good question to me, especially reflecting my career and my experiences. Yes, I am extremely satisfied. There are two things. First, when you think of my career, working in epigenetics, how fascinated I am, how happy I am, how satisfied I am, I would say I'm extremely satisfied. It's a dream come true. Because right from my undergraduate degree, when I was doing my undergrad, I wanted to do a research on cancer, and that it's like I'm living my dream now. And coming to the epigenetics, until my master's, I was not that aware of the epigenetics that time. I now realize when I go to the conferences, there are much more lesser labs working on epigenetics than the other labs. It's because epigenetics compared to the genetics and other many fields is still new, at least newer. That's one thing. And second thing, epigenetics is slightly more complex compared to genetics. It's a heritable changes without change in the DNA sequence. So it's not as direct as genetic. That's why it needs the additional skills, more complex. Being a new field, I feel so proud that I am doing something that matters so much in treating cancer, because there are things that genetics cannot solve, and we need epigenetics. Therefore, I'm satisfied. And coming back to the cure, as you said, now cancer being very complex, we need to go back to the actual cause of cancer. For example, cancer is extremely heterogeneous. The single tumor in the same patient, you have a multiple populations of cells, or the same cancer in different patient is not the same. So in one patient, let's say the lung cancer, it could be through KRAS mutations. For the other cancer, it could be due to p53 mutations, or in other cancer, it could be EGFR mutations, right? EGFR mutations. So that's why we are looking at what exactly is contributing to the patient's tumor. We need to use that specific tools. Therefore, we come to the personalized medicine, individualized medicine now, and then of course, epigenetics has a very important role to play in curing cancer. Of course, finding the targets, finding the therapy, or the diagnostics and prognostic tools.
And also, I believe that there should be the fusion or the intersection of the different technologies, rather than saying that, no, I will just use the epigenetics, I will use the genetics. So it's better to fuse the different technologies to find a cure or to diagnose the disease, I think. Yeah, so this is one thing.
Very true.
And what do you think about the other diseases, other application of epigenetics? We are just talking about the cancer because you are very specific to this abnormality. But what about the other problems? Do you think can be solved by the epigenetics?
Yes, it's a very important question as well. Actually, at the moment, other than the cancer research, I'm also involved in one of the diseases called Gulf War illness.
Okay.
The Gulf War illness is the disease. It's just an example that actually found in veterans. There was a Gulf War in 1990s, and then a lot of armies from the US and the UK went to the Gulf to fight wars, and it's believed that they were exposed to toxins, and we don't have the cure, we don't have the specific prognostic test or a diagnostic test for the disease. So it's all the diagnosis is done through symptoms only, very non-specific, and we don't have the cure. And I'm also working on chronic fatigue syndrome. It's called myalgic encephalomyelitis. It's called, in a simple language, it's called chronic fatigue syndrome. The patient is extremely tired. It's a fatigue.
Okay.
Therefore, I am working on epigenetics of those diseases at the moment as well. And the university has given me a small grant to work on them. Therefore, there are other diseases as well. So, especially epigenetics is, of course, involved in the mechanism, is involved in literally all the diseases.
So this is the application part, and talking about the technology again. So we can see the exponential growth of in terms of the technological advancement in genomics. So is there that kind of exponential growth of advancement in terms of epigenetics technology, or we are very far backward in terms of the technologies?
That's a very important question. I would say it's because the genetics has been such a long history. It was right from the first, let's say, Sanger sequencing invented in 1975. I was not even born that time. Genetics have come a long way that way. And the Human Genome Project, we talk about sequencing the whole human genome. Now, hundreds of organisms have already been sequenced. Right, it's a genetic sequencing, genome-wide sequencing, of course. But now, at the moment, there has been an amazing progress in terms of epigenome sequencing and epigenome or epigenetic technologies. For example, when you talk about the latest one, the next generation sequencing. So, next generation sequencing technology. So we have the same next gen sequencing for epigenome as well. For example, in order to find the DNA methylation in the cells, let's say we use gene sequencing, right, for knowing the sequence. Same way we have, let's say, to find the mutations. So now, in order to find the DNA methylation, we have whole genome bisulfite sequencing.
Okay.
So we carry out the modifications of the whole DNA of the cells, and you carry out the whole genome bisulfite sequencing. The principle is very similar, but whole genome bisulfite sequencing is to investigate the methylation status of the genes instead of finding the mutations. Then we also have, let's say, for the expression, we have RNA sequencing, we have a gene expression array, so we have a DNA methylation arrays as well, right? And then using ChIP-seq, we can actually find out the epigenetic targets.
Yeah.
So there are a lot of intersections between genetics and epigenetics, and there are technologies that you can specifically use for epigenetics as well, but the principle is more or less the same. So I would say we have amazing technologies specific to epigenome as well, but looking at the industries, companies, I think we still have more genetic technologies, more industries, more companies working on them, even more bigger workforce on genetics compared to epigenetics.
But in the end, epigenetics is not just about the methylation, right? So there are different processes which can create the epigenetic change. So do you think the because most of the technologies are based in the methylation, like you said. So is methylation, the checking, just analyzing the methylation process is enough, or do we need to go to the different approach to know the epigenetics?
Yeah, it's a very good question. Definitely, for example, when you think of the mutations in the body and cells, after there's a mutation on a specific gene in cancer or any diseases, then you need to look at what does that mutation does, or what does that mutations do in the cells. For example, does that mutation causes the overexpression of the genes, or the down regulation of the genes. Then you need to go looking at the expression. After that, and then your genetics stops there, more or less it stops there. Then you look into the its phenotypes, and then you look into the proteins, the metabolisms, right? Metabolomics, then you transcriptomics. You go further, and then you use more of the molecular techniques. Same way in epigenetics as well, when you know that there is a DNA methylation in certain genes, that DNA methylation is whether it's it's contributing to the silencing of the genes, it's causing the gene is being turned off or turned on. Then you go further, looking at the expression, and then looking at its phenotypes impact. Then you go to the pathways. You use molecular techniques, for example, Western blots, other immunoblotting, or other techniques. And you take that gene and you go further, more into functional and mechanistic studies. And whether you do genetics or epigenetics, the mechanistic studies more or less are more or less the same. So let's say you when you know that the gene is overexpressed due to the DNA methylations or mutations, either genetics or epigenetics, then you need to think of how to inhibit that gene, right? And then design inhibitor or design the other molecules that inhibits that proteins, and then do the functional studies, right? Treating cells with those inhibitors, looking at the growth of the cells, do the tumorigenicity assay. It means that you re-engineer the cells with those genes overexpressed or down or by knocking down, and you do the mouse studies, go to the clinical trial. So the downstream process after some steps become more or less the same.
But the methyl group is not the only one group which is creating that change, right? So there are different kind of modifications that occur in the histone. Why aren't we going to that approach of looking at the histone modification or other groups rather than just focusing on the methyl group alone?
It's a very important question again. Thank you. So what happens is, so when you look, so when you get a specific disease type or the cells type, then you take the multiple approach in the beginning.
Okay.
Whether you want to find out, there might be a hypothesis or the possibility that there might be the role of DNA methylation on silencing, keeping the genes turned on or turned off first, right? Either turn on, overexpressing that genes, or there might be a gene silence due to DNA methylation. In the same way, there might be the role of histone modifications, let's say either phosphorylation or the histone methylation, and other like ubiquitination as well. Or there might be the role of both histone modifications and DNA methylations together. What our previous research in lung cancer cells, what we found was there is a crosstalk between the DNA methylation and histone methylation on lung cancer, non-small cell lung cancer. What we found was one of the histone modifying enzymes, it's called histone methyltransferase, that actually mediates the histone methylation. It's a protein methylation of the DNA methylations. That histone modifying enzyme actually also, it communicates with the DNA methylation machinery when the gene is methylated. Like there's a histone methylation on that specific region. What happens that it liquids the DNA methylation machinery and contributes to DNA methylation as well. So there might be a role of histone methylations or other histone modifications, or there might be a role of only DNA methylations, or it could be the combined role. Or there might be a chance that there is a genetics and epigenetics involved together. For example, one of the allele of the gene may be methylated, then another allele of the gene may be mutated. Right. So that's why in a cancer, as you said rightly in the beginning before, that we need to take the multiple approach, find out what exactly going in the cell. Is there the epigenetics involved, genetics mechanism involved, or both are involved? Even in the genetics, whether there is a copy number changes, or there is a mutations, right? Or there is the DNA methylations, or there is a histone methylations, or is there a phosphorylations, or other mechanism involved? And you need to take the approaches to solve that defect in the cells.
Just a question about epigenetics and cancer, sir. So you worked on the epigenetics in cancer for a long time. So what do you think, what is the contributing factor for this epigenetics change in the cancer cells? What do you think? What factors are creating this kind of change? Are they more specific change, or the change that is happening, epigenetic change, is just random?
These are very important questions and very critical questions, but slightly hard to answer as well.
Okay.
One thing is we have found that there are global, let's say, methylations in terms of DNA methylations, or some of the changes are global in epigenetics.
Yeah.
But there are changes that are specific to genes, certain genes, right? Specific changes as well. So and then when you talk about what exactly causes those changes, is to an extent it somehow relates to the lifestyle as well. There are in terms of methylation, it's a methyl group, right? That's there are certain sources that provide the source of the foods, the lifestyles that provide source of the methyl group, for example. So there are methyl group donating foods, and then other lifestyle factors. For example, what we have found is the people who are based mainly work on night shift have a higher chances of having cancer than the day shift.
Okay.
So it's amazing, right? And there are certain populations, for example, the people in Australia have a higher chances of skin cancer.
Okay.
And the people in US have a very high chances of breast, lungs, and other cancer. In South Asia, there's such a huge number of cases of liver and pancreatic cancer as well. For example, in the US, I give an example of this a lot, that the gallbladder cancer is among the top 20, but in Nepal, that we are working on now, local gallbladder cancer a bit, it's among the top 6 in South Asia. It means that, so because specific cancers are somehow involved with specific gene changes, right? That effect on those, switching on or switching off those specific genes. And these are a kind of genetic predisposition, available that we can find out. Therefore, it's both. Some of them are very random.
Yeah.
And then we need to find out which are those random, right? But mostly what we need to find out is what are those changes that contribute to the specific cancer types.
Yeah.
Or specific populations.
Yeah. Like you said, the in Australia there is more cancer cases, the skin cancer cases. So is it very, like we can say, is it very specific to certain gene? The epigenetic change is very specific because of the sun exposure, or is it not? So I think this is a matter of the subject of a big research of finding out whether, because we always say that the epigenetic change is happening, but we don't know. I don't know if some researchers are already doing it, the research which is more based on whether this is more specific or not. So, but I found it quite a very attractive subject for the research.
Yeah. So what happens is that when you, one of the major challenges for the cancer is that in the same tumor types, so the same cancer, or the same diseases, there are multiple phenotypes, or multiple group of patient. So one group of patient might have the roles of epigenetics.
Yeah.
The other group of patient might have the role of genetics. For example, you may find the specific group of patient with the skin cancer, which are we got a cancer. When you got back to the root, it could be because there is a the histone methylations, the role of histone methylations, or the role of DNA methylation on certain genes. Right, those genes are either those genes are defective because of the histone methylations or phosphorylations or the DNA methylations, or in other group of patients there might be chances that specific some of the genes are mutated, and that might be the cause of those
epigenetic
diseases. So therefore, we need to, when you look at the specific group of patients, the phenotypes, then we will know what exactly might have happened in those patient population.
So a few days back, I was just exploring about the startups, mainly based on the technology they are using. Mostly, specifically, I was focused on the epigenetics startups. So the startups which were using directly or indirectly epigenetics as an application or as a technology. So I found several startups. They were diverse. and they were mainly solving the problem of aging. They were mainly funded by the VCs and funded by also the investors from the software industry like Jeff Bezos. That's the matter of interest. Epigenetics and cancer, or epigenetics and aging or longevity. There were many founders. So if you are comfortable, I would like to discuss about some of the business side of the epigenetics, if you are comfortable. So if you have closely observed this kind of startups growing, so what do you think about the startups? So are there enough startups, or can we make a startup out of the epigenetic, the lab which are working on epigenetics, and what kind of problems do you think we can solve and take it to the market very soon?
I haven't done a lot of research on there, but there are a few things that I can tell as an epigeneticist.
Yeah.
We have some renowned epigenetics company. For example, Zymo Research is one of them, for example. And there are other well-established companies are also started to add epigenetics component to it now. The well-established companies also have an epigenetics division these days, and they are working because when they develop technology, then they started now. Okay, let's work on epigenetics as well. And I also find, going back to questions, is it possible to start some startups on epigenetics? I would say, of course, yes. Compared to the other companies, I also feel the epigenetics companies are much less in number. We are much less epigenetics companies compared to other companies in other fields like genetics.
Yeah.
So, for example, 2 months back, on end of November, I went to the conference in DC, Washington DC. It was the American Society of Human Genetics conference. So over there, I found that there are such a huge number of companies that I met and talked to them. They were mostly on genome sequencing, next generation sequencing, and there are very few of them who are actually working in epigenetics.
Oh, okay.
And because I am now working on cell-free DNA from the patient, but I'm trying to look at the epigenetic dysregulation of cell-free DNA in the patient, and then it was very hard for me to find the right companies who could help me with to process the cell-free DNA, to looking at the whole genome bicycle sequencing. Let's say the library preparation, the sequencing, getting the right amount of DNA. For the epigenetic studies. So then I realized, of course, we have a lot of opportunities. If you have the skills set for specific things, I think you can take that further to work on to establish a startup and then develop that specific technology that is lacking at the moment. I do feel that, for example, one more example is at the moment I am working in exosomes. Okay. So I'm taking patients' plasma and trying to isolate exosomes. And after isolating exosomes, free floating vesicles in the patient's plasma. And then when I wanted to have a cell-free DNA isolations from those plasma, getting a good quality cell-free DNA is very tough, to be honest. And there are a few companies whose kits is not the best, as I expected. So you are, what I feel is you still have a chances to, develop technologies for the, isolation of DNA, RNA, proteins from the most challenging samples. You still have a chances working on that front.
So, and we always say that epigenetics drive the gene expression, but can we say the gene expression drive the epigenetics? Can it happen?
Yes, very much, because let's say one of the genes is overexpressed, or let's say the proteins are overexpressed. However you take, when you talk about genes overexpressed or the gene is downregulated, its protein product becomes overexpressed or downregulated, and that contributes to the epigenetic regulation of downstream gene, of course, right? So yes, it does.
Okay. So, sir, so let's talk about NIRI for some time. So, what is NIRI, and what is the goal of NIRI in Nepal?
Yes, thank you for this question. This matters a lot to me, right? NIRI is basically, it's a Nexus Institute of Research and Innovation. It is established by a group of professionals, basically Nepal-based Nepalese professionals, I would say, or the professionals of Nepalese origin who live around the world. We have 35 members. Most of them are the scientists, the researchers. and they live different parts of the world. So we came together during pandemic, the COVID pandemic, and then we thought it's a very high time that we establish an organization in Nepal dedicated to research and training young professionals. And also our goal is to help government in policy making and to translate our research finding into the products of the clinics. Now, so it's been 3 years that we established. It's been 3 years since we established NIRI, and we have been able to organize workshops, boot camps, and then hire some research interns to work on certain projects. And our goal is to train. One of the goals is to train young minds to be able to develop skills, globally competitive skills, so that they can utilize in any countries, in research or clinics or academics or industries. So that's all about NIRI. It's basically registered in Nepal, and we also have we are in the final process to get 501c, a non-profit US partner as well.
You are also closely looking at the research ecosystem, research or startup ecosystem in Nepal. So what do you think are the problems in the research that's happening in Nepal? And do you think we can ever be able to translate the academic research into the product or the business in Nepal? So how difficult is it? And
yes, I have, of course, being a NIRI member. I also chair NIRI at the moment as a founding chairperson. So I definitely we NIRI team together are closely watching and closely, I would say, experiencing the research ecosystem in Nepal, of course, and we are part of that ecosystem already. So what we have found is that it's extremely challenging to do a good quality research in Nepal, but our goal is to overcome that challenges and help government, help stakeholders, and work together with Nepalese professionals, other research organizations, and other research professionals in Nepal to overcome that challenges as well. Basically, one of the major challenges that I find is to get a right policy in hand. For example, even for the clinical trial at the moment, we need to go and take the approval from the Minister of Council. It's not that I don't think it's that friendly approach, right? This is not the right approach. I mean, just to get an approval of clinical trials, we need to the Council of Ministers have to approve that, and this doesn't sound right. Number one. Number two, importing goods, the equipments, it's very tough. There are hurdles in the custom to import the equipments for the research. There's a high tax and other hurdles. Third, we don't have support from the government. We don't have the definite funds from the government that are dedicated to the research. And fourth, there is NHRC, National Health Research Council, which is the only body for IRB. It's very centralized, and that's very tough to get into the IRB, the ethical clearance and time. And also it charges quite a high fee. That doesn't seem very all right. And one more challenge that we have is that NIRI is not a profit sharing company. It's a private, not sharing institution, not a profit sharing institution. So we used to have NGOs before. Then NGOs is not very right for research. It works very differently. And now the organizations like NIRI, which is not a profit sharing company, it's handled by both Social Welfare Council and the company office or company register office. So it's neither. It's like almost like abandoned. Neither Social Welfare Council solely takes care of it, nor the company register office. Company register office is actually for profit-making companies, right? So we are like middle profit-making companies and Social Welfare Council, both regulating the non-profit sharing research institutions in Nepal. So it's tough, but only way is to work together, help government making more friendly, more conductive, policy making, research conductive policy making, and overcome the challenges together. Good quality research can be done in Nepal.
So you mean the technologies which are needed for the startup, so they can be built in within the country? So is it possible?
Yes, definitely possible. For example, when you talk about next generation sequencing, one of the state of the art technologies now,
Yeah.
this is we can, of course, if you do a startup, we can buy, of course, process machines. We can, if you have skills, you can run that in Nepal, right? The technologies or the equipments that is built in one of the part of the world can be
Transferred, yeah.
access that, transfer to Nepal and establish there. Only one thing is that we need skills and we need funds, and we also need the good kind of support from the government, or we need to work together to remove the hurdles, to overcome the hurdles. For example, if you are having the not-for-profit sharing company, then it's not fair to pay tax, very high tax, to get those equipments. That's solely for the research, right? And the research funds come from taxpayers' money, and so we need to have government policy in hand where it supports the research institutions for research, right?
What I think is that the government policies could be one factor, but there should be also synchronization between the private bodies too. I think the private bodies, they are not interested in the Nepalese research, and because they have not seen any examples, the success examples in the biotech industry. They might have seen examples in the software industry or the IT sector in Nepal, but biotech is a very new sector. So I think there is also the very less interest from the private sectors. So that is also causing the problem in the funding part. That's happening in Nepal, I think.
Yeah, that's very true. That's very true. And you actually raised a very good point that because IT sector is very, it's easier to make people understand what's IT. But it's very difficult to make people understand what's biotech, and it's important.
Yeah.
I think the COVID pandemic, I know it was not a good news, but after we had a pandemic, I think it has somehow played a good role to make general public understand how important the science, biomedical research is. So now everyone, literally anyone who never studied science, who have no idea on science research, now understand what is PCR, how important it is, right? The lab test, PCR test. So what I mean to say is that when skilled manpower is skilled to stay in Nepal and establish startup or to work on that front, I think if they have good skills, I think it's easier to convince people. And then one big opportunity could be the outsourcing, like because Nepal being a little cheaper in cost.
Manpower.
I think the multinational companies, big companies, international companies here, or multinational companies here, biotech companies may outsource some of the work in Nepal, and that could be a starting point as well.
That could be, like I think it should begin from somebody who is already working in the high post in those big pharmas. I think they could initiate, and that would be a good start, rather than somebody who is just a student or just a PhD graduate doing from scratch. I think somebody who has a good connection with these big pharmas, they can start, I think.
Exactly.
I also think that there are several difficulties, but there are also the possibilities, like when we talk about the cost and when you the environment or the I think we don't lack the skilled manpower, but we don't know how to utilize them. So that's the thing that we are lacking in.
True. Otherwise, one point solution is that one of the very important things that we need to do is, as you rightly said, I want to get that word back, that it's a synchronizing among the private companies and synchronization among the professionals, research professionals who are interested working in Nepal. Either they are in Nepal or abroad, at least those individuals, research professionals and biotech sectors that wants to contribute to Nepal. If those people come together, I think some of the people who are already in big pharmas here, or big industries here, they can help from here. And those who are interested to return home can return to Nepal and collaborate and work together who are here in abroad. That way, I think the synchronization and collaboration together would make life much easier, the research easier. And the NIRI is established with that actual emotions in hand, that we wanted to work together to do a world-class, high-quality research that's more relevant to Nepal, something that's relevant to Nepal, and that's a global, Nepal and beyond, basically. So that's the goal, and that's why I think I want to take this opportunity that NIRI is open to collaborations, and we believe it's a collaborations that make a successful research. So we're open to, open to talk to, work with anyone they can join us as the member, as a collaborator, if they want to write grant or join NIRI or work with us in collaborations, we're extremely open. And so that's.
And I also feel very privileged for getting that opportunity during the start of the NIRI. I was also there. I shared my journey there. So I think we are in the end. So what suggestions do you want to give to the young scientists or the young graduates who want to go to the top universities in the US or want to do the PhD? So what is your suggestion for them who want to do something in epigenetics and the cancer?
What I suggest the young minds or the youngsters is that you need to think in advance when you think of a career. For example, what I find, especially the people in developing countries mainly, as I am from one of the only developing countries, Nepal, that or any part of the world, any youngsters in any part of the world, so they need to plan their career in advance first. That it's not necessary that they have already decided that which field they want to pursue. But regardless of that, they need to start volunteering in organizations right from their high school. And in the US, especially during your undergraduate admission, your involvement as a volunteer or a research intern is one of the major factors here, one of the major points that you get admission. Therefore, in the US, so right from high school, the students start to volunteer in the research lab, in hospitals, in clinics, in other care homes, and in either zoo or national parks or anywhere, so many places to name. So in last summer, one of the high school students came to me. He approached me, and then we took a formal approval from the university, and he volunteered 3 weeks in my lab. He actually, being a high school student, he exactly did the things that I'm doing in the lab, the same technologies, same process, same methods that he learned. So during this New Year, just 2 weeks back, one of the high school student from California, she came to Florida over here. She stayed for a week in Florida and she volunteered in my lab. Right. What I mean to say is that, so you need to volunteer or work as a research intern, learn the techniques. Then there might be a chance that you don't know what you want to do in the future. Then your volunteering, your internship will give you an opportunity to decide what you enjoy most, what you want to do. So it also helps you to decide. Therefore, my suggestion is to gain skills, right? Work as a volunteer or research intern. If you get a chance, even join work and get paid, get a little money, gain experiences, gain networks, and that would help you a lot in writing your personal essay, your journey, your experiences, and that is one of the major factors in getting to a good university. So you need to have a good marks, of course, good grades. Other than that, it's not only grades that determines your admission. So it's your involvement, your passion, your responsibilities to the community work that you do, right? And how can you use your skills and your education for the community? That's one of the factors as well. So that's my suggestion.
Thank you so much, sir. Thank you. Like you said, the education, always education, and the experience and the network can take you a long way. So
thank you so much for the opportunity, Sudarshan, and it was great speaking with you. And let's keep in touch and let's keep collaborating. Thank you very much.